countdown, we'll be ready to go. Now, we already done example 1. That's just because example 4 and 5 aren't in the thing. 2, 3, 4, and 5 weren't in the thing, so we'll be using this white space. But before we do, I think I was telling Charles earlier when he was the first one here, I came this close. In fact, I thought I had finished fall schedule. I mean, Friday, I finally got everything pretty much lined up in place. Oh, and by the way, I need to tell you, you had pre-registered for Physics
1 and Cal 3.
And Cal 3. They had both of those at the wrong times. So I pulled you out of both of those, fixed the times, and put you back in. So the schedule is not as you saw it, but it's as it is now. So when you go to pay, you'll notice the times have changed. And I think they had Dr. Bryant teaching Cal 3 too in the day, when he usually teaches Cal 2 at night. So that was all wrong. Now I'm teaching Cal 3 and he's teaching the physics, and I adjusted the time. So I think you'll be okay now that I think about it, because I did do that on Friday. I didn't have to override anything. So I think the times worked out okay for you.
What are the times?
I don't remember now, but Cal 3 is sometime late morning, early afternoonish, and Physics 1, I think, is late evening, which you might be disappointed. Not late evening, but in the evening. The reason is what we do, every term we flip-flop Physics 1 and Physics 2, because that way if the evening crowd is taking Physics 1 then in the fall, then they can take it Physics 2 in the spring. If they are taking Physics 1 in the spring, they can take Physics 2 in the summer. So we flip-flop every time so they can have continuity, and then the day students can do the same thing. They can have continuity. And if it doesn't matter, you have continuity. So, but we do that way, and they hadn't done that when they brought the schedule in, and that's before I had a chance to change it. You had already registered, or pre-registered anyway. So anyway, I think you're okay. I think you're, yeah. You may not like the physics being that much later, but that's when it has to be for the evening students. Okay. Okay, so I got that done. So then I proceeded over the weekend when I had time. We had a pretty busy weekend, didn't have lots of time. I finally got all my last tests graded. They had been sitting there lingering while I was working on schedule. So I finally got them all done. And I came that close to starting grading yours, but ran out of time, energy, and just ran out of everything. Last night, I just couldn't do any more. So hopefully today, knock on wood, I'll be able to start work on the rest of this big pile of stuff. I got one big chunk out, but I've got several big chunks left to go. Okay, now nothing's in Blackboard yet, not for a long time. I've got to get these graded first before I can put things in Blackboard. All right. Now, it's kind of a good news, bad news situation, a bit worse on the bad news, I'm afraid. If I'm not mistaken, next Monday is Veterans Day. And the two-year college system, that takes that as a holiday. So that's the good news. We're celebrating Veterans Day. The bad news is, means we won't have class on Monday. Sorry about that. Get over it, okay?
Well, that's really, we can still meet, like somewhere downtown, like Starbucks or something.
Yeah, why don't y'all do that, okay? Okay. Tell me how it goes, okay? Wish we could. Because I don't even know if we'll be in town. I know you're being facetious. Okay. All right. Any questions before we proceed? Okay. We're making pretty good progress in Chapter 7, which is Applications of Integration. We're in 7.4, which is arc length and surfaces of revolution. And, I forgot to tell my first class, But I'll tell y'all, what's tomorrow? Vote, 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 vote. Okay, good deal. All right. Example 4 is on page 477 in section 7.4. And this one's also located at larsoncalculus.com. If you want to see an interactive version of this type of an example, go for it. So it says here, find the arc length of the graph of y is equal to log, ln log, natural log of cosine x. All right. Now, in order to find arc length, there's a big, long series of steps to get there. What's the first one? Or maybe what's the formula for arc length, and then we can back off the steps from there. What is the formula for arc length? Usually we give it the name S is equal to what? Oh, I didn't finish writing the problem down. Find the arc length of the graph of that thing from x equals 0 to x equal pi fourths, as shown in the figure. Okay? I'll let you look at the figure. Okay. So what's your formula or description of how to get an arc length? I know it was a long weekend, okay? At least 5 days since we met. Okay, yeah, you use the distance formula in a sense. How does that go?
This is going to go straight to the arc length. It's how the arc length.
What's that?
Are we going straight to the distance or the arc length?
Arc length, yeah, but it's based on the distance formula. Okay. Okay.
S is equal to a to b square root of 1 plus.
Square root of 1 plus.
The derivative of
F prime. Right. Squared. Dx. Okay. And from a to b for us would be from 0 to pi fourths. Okay. Now, that's where this would be our F. You could have, if you wanted to write it differently, you could have put y prime in there. That would have been the same thing. You could have left it as y. So what's the first thing? In fact, let me go and do that. Is that okay if I do that? Because f and y are the same, basically. So let's just call this y prime squared. So what's the first thing we've got to do?
Take a derivative.
Take a derivative. Good deal. Okay. So your y prime is what?
Remember, I think it would be. Go back.
Take the derivative of natural log. Anybody? A little louder, I can't hear.
You're good. I don't know, something just threw me off when we drew the line from the denominator. It looked like he was trying to take an antiderivative for a second. That's wait, why is he drawing an antiderivative? We're taking a derivative.
No. The derivative of log is, if that was log x, what would be the derivative of it?
1 over x.
1 over x. So this will be 1 over cosine of x. But then we've got
the times negative sine.
Times negative sine x. Is that okay to do it that way? Okay. So there's what we've got. Minus sine x over cosine x. Now, there's a real tendency to say, well, let's just name that tangent squared. And that'd be okay. I mean, negative tangent x. And that would probably be all right, too. In fact, that might be a little easier. So you want to do that? Yay or nay? Okay. Let's call it negative tangent x. Let's see if that works okay. What's the next thing you do with it once you have y prime? Well, yeah, but square it first, right?
Oh, right.
Y prime, then you square it. So y prime squared is equal to?
Negative tangent squared.
And what's negative tangent squared? Negative times negative is? Positive tangent squared x, right? Everybody agree? Okay. Now we do add 1 to it, right? 1 plus y prime squared is 1 plus tangent squared x. Okay? Now, we take the square root of that, right? So let's take the square root. But what is 1 plus tangent squared x? Oh, where my voice went? Okay. What is 1 plus tangent squared x? One of those good old... Anybody?
Secant squared du.
Second?
Secant squared du.
Okay, I think you're doing a little bit more. I'm just saying, what is 1 plus tangent squared? And that is secant squared. Okay, so this would be the same as the square root of secant squared. Okay, x. Okay, and what's the square root of a square? Itself. So that would be secant x. All right. So here we have the integral from 0 to pi fourths, but a big boo hiss, secant x isn't a direct derivative of anything. So I think rather than writing it as secant x, I want to write it as let me think just a moment if this is going to help any. This almost seems like we're running in circles here. But I want to write that as 1 over cosine x. Does that help us any? I don't think so. Okay. So let's go back to just calling it secant x. Okay. I thought maybe that would help us, but I think we need something else in there. So let's just call it secant x. Now, that's not one that, yeah, I think we did do it now that I think about it. We did do the integral of secant x. But that's not one I always commit to memory. If I need it, I'm going to look it up. So let's look that one up. What is the integral of secant x dx? And it may be when you, as soon as you see it, you'll say, oh yeah, I know what that is. Antiderivative of secant x. It was one of those sort of weird ones. You did a lot of strange stuff too to get to it.
Secant x times tangent x.
Okay. Not times, is it? Integral of secant x is that what you're doing? Integral? You're doing derivative of it.
Yeah, I guess so, yeah.
Oops. Okay.
The log of the natural log of secant x plus tangent x plus c. Well, for ours would be plus c.
Okay, because we have a definite integral, we just evaluate it between 0 and pi fourths. Okay. Now, normally that has absolute value bars around it, right? But guess what? Where are we, Waldo, if we're between 0 and pi fourths? Where's that?
Positive.
First one, right? What's in the first? What can you tell me about the trig function in the first quadrant? All positive. So you don't need absolute value bars because these are all positive there. So you don't want to take the log of 0. You can't do that, and you can't take the log of a negative number. That's why they put absolute value bars there. But guess what? First quadrant, none of the trig functions are negative, so these are going to be positive. So this will be the log of, and does anyone know what secant of pi fourths is? If not, we'll come back and do that. Let's just plug in first, plus tangent of pi fourths minus the log of secant of 0 plus tangent 0. Right? All right. Now, I don't keep in my head what the secant of pi fourths is, because I know secant is reciprocal identity. What? No, secant. Those go together in Pythagorean. But the reciprocal identity, what is that? Cosine, exactly. And what's cosine of pi fourths?
Root 2 over 2.
Okay, and if you invert that, you get that's what the secant is. It's just root 2. How did you get root 2 over 2? You had 1 over root 2 and blah, blah. So it says cosine is 1 over root 2 of pi fourths. This is just root 2. So secant, remember, is always greater than 1 or less than minus 1. Okay, so root 2 fits the bill there. So this would be the log of root 2 plus, and what's log of tangent pi fourths? I don't think so.
Root 2 over 2 times.
Divided by root 2 over 2, which is 1. Yes, okay. Okay. Minus the log of, what is secant of 0?
Cosine of 0. That's it.
What's cosine of 0?
1.
1. So secant would be 1 over 1, which is 1. So one and only place that it is equal to 1, I mean, each cycle, each period. And what's tangent of 0? No, pi halves is undefined. Tangent is, what's the ratio identity or the quotient identity for tangent? Sine over cosine. What's sine of 0? 0. 0 over 1 is 0. Okay. So that would be plus 0. So I'm just going to do, and what's log of 1? Nope. Log of 1. Log of 1. Anybody? plus log of 1 is 0. So that's nothing. Okay. A lot of zeros here, weren't there? Okay. So this is, your answer is simply log of root 2 plus 1. Natural log of root 2 plus 1. And root 2 is about 1.414, and plus 1 would be 2.414, and that would be log of that, whatever that is. I don't care, really. 0.0881, you got it. So, there's example 4. All right, that's the arc length of good old, I always wonder what the arc length of log of cosine x was, you know, between 0 and pi 4. So I stayed awake at night trying to figure that out. Okay, so let's move on to example 5, which we're going to have to do on the same white space. So let's erase all this. Everybody got it? No one needs it a little longer? Okay. So, example 5. The length of a cable. An electric cable is hung between two towers that are 200 feet apart. Y'all all got books, so you see the drawing there. And they happen to put them not at 0 and 200, but at negative 100 and 100. Okay, fine, we'll do it that way. The cable takes the shape of a catenary, whose equation is y is equal to, one of my favorite equations of all time. This happens to be 75 because of this cable. That is not part of it. E to the x over 150 plus e to the minus x over 150 and that's the same as 150 times the hyperbolic cosine of x over 150. Okay, guess what? I don't even care about that. Okay, fine. But let's just deal with the first part. I like exponentials. Hyperbolic cosines are fine, except I always have to look them up. I can usually do exponentials in my head. Okay, because hyperbolic cosines differ from hyperbolic sines only by a sign here and there, but not in other places. So I always have to look them up to make sure I got the signs right anyway. So why not just use this?
What does hyperbolic mean?
I don't know why they use it. It's a it's a function that's defined just like this. It's e to the a plus e to the minus a. 2 times that is or 1/2 of that, or something like that, is hyperbolic cosine. I mean, it's just a name they give it. The reason I don't know why they chose hyperbolic. They're not like a cosine function, except that the derivatives are similar to that of cosine, except where they differ by a sign. That's what I said. I have to look them up anyway, because I have to remember, does this sign change or not change, you know? I think I could figure it out on my own. But it's so much easier to use exponentials than to come up with a new function and then have to remember the new function. It's shorter and more concise, but you still have to look it up. I can do that one without looking up. So what else I have to do?
Take a derivative.
Take a derivative, exactly. Find the arc length of an electric cable is hung between, shown here. The cable takes the shape of catenaries, whose equation is, and so that's the arc length we're looking for. Okay, so our y prime. Okay, now okay, they skipped some steps here, so let's just go straight forward. What's derivative of the first? 75. Huh? Is itself, which is x over 150. But then you got the chain rule. What's that?
I thought 75 was 0.
Okay. Okay, 75 isn't 0, it's 75, but I know what you're saying. The derivative, right?
Yeah.
Okay, but that's not the chain rule I'm talking about. This is the coefficient for this, right? So the coefficient you bring down. Okay. The chain rule is the derivative of the inside, not the outside, the inside. Well, what's the derivative of x over 150? That's it. What is the derivative of 1/2 x? Anybody? What would be the derivative of 3x? 3. The derivative of 1/2 x would be?
1/2.
Derivative of x over 150 would be?
150.
1 over 150, right? The coefficient. Okay? So that's where you get 1 over 150. Okay? And here you would have, you can multiply the 75 times that 2, or just do derivative of that. I like to do it. So let's do, okay, let's just do it both ways, okay? Plus, what would that derivative be? $75
So again,
yeah, 75e to the minus x over 150, and then the chain rule part would be negative 1 over 150. Okay, that would make that a minus, and this a 150 in the denominator. Okay, and this would be 1/2 e to the x over 150 minus, pulling out the 1/2 e to the minus x over 150. And by the way, that is not that you need to know it, but just to let you know, this is 1/2 hyperbolic sine of x over 150. Okay? Not that you need to know that, but it is. Okay? And see, the derivative of hyperbolic cosine is positive hyperbolic sine, not negative hyperbolic sine. That's what I said. They're very similar to the trig functions, but not. You know, sometimes there's a sign change, sometimes there's not. And this one isn't. But you don't need to know it. That's not necessary here. But all you wanted to know was this. So the next thing we're going to do, that's your y prime. What's the next thing we do? Square it. So y prime squared is this thing squared. And what would that be? 1/2 squared is? 1/4, yeah. Okay. Now, to square that, you square the first term, which is e to the 2x over 150, which would be x over 75. You buy that? Okay. Then you got a minus twice the cross product. So minus 2 times e to the this times e to the that. Well, e to the this first thing, and the second is 1 over e to the same thing. So you have the product of e to the that over e to the that, which is 1. So that's just a minus 2. And then you have a plus e to the minus 2 times that. You're squaring that, so that would be x over 75. So there would be your y prime squared. Okay? Was that too esoteric? And you see at this point, you see hyperbolic sines and cosines really aren't doing you any good anymore. The exponentials still work well. Okay. Now, next thing we do is, yes.
Over the negative 2 again.
Okay. All right. Let's go up to the top here and do e to the x over 150 minus e to the minus x over 150. And you want to FOIL it? Is that okay? E to the x over 150 minus e to the minus x over 150. Okay. We're multiplying those two. So first times first is just simply e to the 2x over 150, right? So that would be x over 75. That's where we got that first term. Okay. Now, let's do the outers. Okay. Now, the outers here would be, this is going to be a minus. Okay. That would be e to the x over 150 times e to the minus x over 150. Well, that's 1 over x to the 150, so that would be e to x over 150. That's, this thing is 1 over e to the x over 150, right? So when you multiply those two together, multiply e to the x over 150 times 1 over e to the x over 150, you get a minus 1, right? Because that's, you told me that's a 1. So this is a minus 1. Okay, we'll come back and write that in a minute. Let's go over here. I don't want to write on top of the other stuff. Not that it's ever stopped me before. This is the same deal. E to the x over 150 times minus, so that's another minus. E to the 1 over x over 150. Guess what? That's another 1. Right? You see it?
Yes, sir.
Okay, and then you have a plus e to the minus 2x over 150, which would be x over 75. Okay, so that's where you got the minus 2. The minus 1 from here and the minus 1 from here. That gave us minus 2. It's magic is the answer. Right?
Almost like quantum mechanics almost.
What's that?
I said almost like quantum mechanics, so I know that's what he's saying.
I'm curious with that.
It almost just like quantum mechanics.
Oh yeah, I wondered if that's what you were saying, but yeah, it's magic. Just disappeared or showed up or whatever, you know. Okay. So what's the next thing you do to y prime squared?
Square root.
Not yet.
Add 1.
Add 1 to it. Okay, so we're going to add 1 to that. That sounds pretty innocuous, doesn't it? Okay, so let's just add 1 to that. All right. I'm going to add that 1 as a 2 halves. Is that okay? That's 1, right? It's magic again, but yeah. Okay, but that is 1, right? Okay. Well, the first term here would be e to the x over 75, I can't write, over 4, right? The next term was going to be a minus 2 over 4, which is minus 1/2, right? And the next term is going to be plus e to the minus x over 75 over 4, which you could have written another way, plus 2 halves, right? Well, minus 1/2 plus 2 halves makes it plus 1/2, right? So, now we take the square root of that thing. So it's going to be the square root of, I'm going to rewrite it as, alright, for me to factor out my 4, because I don't like it anyway. And it's 1 over 4. So it's going to be, this is 2 over 4. So all those have a 4 in the denominator then, right?
And where did our 4 come from?
From that 1/4 up front.
Oh,
okay. Okay, now I changed it to halves, now I'm changing it back to fourths. Yeah, right. Okay. Some of this is really ugly now. I can't get it to, there, erased. Okay. I can't get my pen back. There we go. Nope, still not. There we go. 2/4. Remember when it was a 1/2. Yuck! Quit. Okay. Okay. Now, if I factor out the 4, 1 over 4, square root of 4 would be 1 over 2. So that's the 1/2 out in front again of a radical. And what we have under the house now is e to the x over 75 plus 2 plus e to the minus x over 75. Okay? Okay. Now, what I want you to do a flashback here where we did our squaring this term to begin with. Yeah, squaring this term right here. When we squared that term, we got a minus 2 in the middle, right? Now we got a plus 2 in the middle. Now, what made that a minus? The minus here. So, what's going to make that a perfect square is it's going to be this thing plus this. That'll give us that same result, right? With a plus here. So now we know what that is. Now let's go back and write our formula. Your surface area is, which is the length of the cable, the integral here's the thing I really don't care for too much, but I think it's okay. If you look at the picture in the text, you see that the 2 towers at minus 100 and plus 100. That 150 up there, where that came from, they haven't said this, but this is the only thing that I can assume here, and then also knowing what catenaries are like. That 150 means that's the 150 on the y-axis, is right where that's bisecting it. Okay, I can't think of any other reason. And I thought, why in the world, where did these 150 show up? That's where it showed up. That is when x equals 0, y is equal to 150. Okay? Now, why did I go into that? Not too sure, except that, just to explain that to you. So what we're doing here is integrating dx's, right? Okay. Well, take a look at that cable. Don't you think the same length is to the left of the y-axis as to the right of the y-axis? So let's just make this double it. Let's double the integral from 0 to 100, so we don't have to do minus 100 to 100. I'm lazy enough not to want to do that. And then this will be our formula for the rest of it. And this formula would be the y prime, everything that we've done so far, that 1/2 comes out front, so that loses a 2, right? Nice. And this would be the square root of e to the x over 75 plus 2 plus e to the minus x over 75. And then we'd have our dx, right? Because that was our square root of 1 plus blah, blah, blah. And we've already said that would come out being, wish I had more room. The s is equal to integral from 0 to 100. And this is just a perfect square of e to the going back the other way, so I think it comes back to the 150, doesn't it? X over 150 plus e to the x over 150 dx. All right. Yeah. Okay. Now I hope we can make our integration now. What's the antiderivative of e to the x over 150? E of x over 150 times 150. Yes. Okay, that's a times there for that one. Okay. And then this would be antiderivative of that. Oh, I left off my minus sign. Okay, because that was a minus sign there. What would that be?
Minus
150 e to the minus x over 150. Okay, and we evaluate that from 0 to 100. I need more room. So what I'm going to do is erase that at the top. Is that okay? We already got everything out of that we could, right? So let's erase this if I can get my eraser to work. It's not working. I think I've got too many things out there. There it goes. And it erased what I didn't want to erase and didn't erase all that I did want to erase. But that's sort of your story of my life, okay? Okay. Okay. What we're doing is evaluating that thing right there from 0 to 100. Okay? So let's put 100 in there. You get 150. E to the 100 over 150 is 2/3. Everybody buy that? Minus 150 times e to the minus 2/3. Minus, plugging a 0 in, 150. What's e to the 0? 1, okay. Plus 150 e to the minus 0, which is still 1. Well, even though those had 150s, they add to 0. I hope. Or do they add? Wait. These signs will reach out there and grab you where you don't want to be grabbed. Let me see. Okay, we plugged in these, and that gave us okay. Now we're plugging in the 0 down here. The first one, that, and your minus, because it's the lower number, minus the 150 times 1. and then there's a minus, the minus. So I think that's okay. I believe that is. I get headaches thinking of all these minus changes swapping back and forth. Let me just see. Yeah, those add to 0. So then you have 150 times e to the 2/3 minus e to the minus 2/3. Okay, that is our answer. Okay, now that requires a calculator. No way I'm going to evaluate that on my own. My 2/3 didn't show up too well. There's the 2/3. Okay, so if you get your e to the 2/3 minus 1 over e to the 2/3, you get some number. A positive number, by the way. Fairly small positive. No. Actually, minus a small number will be a large plus will be fairly. I don't. Okay.
215.1475.
That sounds approximately 215 feet. We already took care of doubling it when we took out the 1/2. So yeah, that should be our answer. All right. A lot of math involved, huh? The calculus wasn't too bad. It's the algebra and the evaluation, the arithmetic. When you do the e's and the minus, all that other stuff, that can really get it. Some of the calculus was a little hairy, but not too bad. Okay. Whew. All right. Now we're ready for area of a surface of revolution. Okay? Now, what have we done so far in this section? Arc length. That gives you how long the thread that function is. Okay? If you revolve that around or rotate that around an axis somewhere, the x-axis, any axis, then what you get from a line, a curve rotated around, you get a surface. You don't get a volume because there's nothing under that. You just get a surface. So this is what we're doing here. Definition of a surface of revolution. When the graph of a continuous function is revolved about a line, the resulting surface is a surface of revolution. Okay? Now the area of a surface of revolution is derived from the formula for the lateral surface area of the frustum. They misput frustum. I think there's an R in there, if I'm not mistaken. No, frustum. That's what they're calling it. I thought that was frustrum. I've been saying that all my life. The frustum of a cone, okay, of a right circular cone, okay. Oh boy, not one of the things I tend to want to remember. The area of the frustum of a right circular cone. In fact, I don't. Okay. But here's what we got for that. Consider a line segment in this figure. There's that line segment, L, capital L, where L is the length of that line segment. R1 is the smaller radius, R2 is the bigger radius to make the cone, a portion of the cone. That's what they mean by frustum. It's just a portion. Cut off one end at the other end. And this is a frustum of the cone. Radius of the left end, radius of the right end. Okay, R1 and R2. Okay. Now, if you revolve that around the, say, whatever the axis is that those are measured, the R's are measured from, then revolve it around there, then you have the area is the area of revolution. Okay. Now, when the line segment is revolved about its axis, it forms the frustum of a right circular cone, and that surface area is 2 pi r times the length of L. Of course, you're just doing that length and doing it around its circumference, which is 2 pi r. Now, but what is that r? That r is exactly half the average between these two. Just think of it that way. So let's go back to the picture. Let's just take the average value of those two, which would be right about there, and let's just do that around here, and that would be very similar to this, wouldn't it? Just take that line and pivot it right on the center point, and you got it, okay? And that would be the surface area of that frustum, where r is halfway between those 2 points, the average radius of the frustum. Okay, consider the function f that has a continuous derivative on the interval from a to b, one end to the other end. The graph of f is revolved of the x-axis to form the surface of revolution as shown here. So here's now your curve. No simple little frustum, no cone, anything else, but any dx here is going to approximate a dl here. That will be not the same length as this, but awfully close to it, right? Okay. So your y value here is your R1, the y value here is your R2. Half of that would be, the average of that would be the sum of those divided by 2. So this would be that little gold belt around there, which looks awfully close to the frustum of the cone. And you're integrating from a to b, and you can just let your dx get smaller and smaller and smaller, and that gets closer and closer and closer to being actually the lateral surface of a frustum of a cone. So you're getting a much better estimate, and that gives you basically your integral. They're probably going to take it through some summations first, but let's see. Let delta be a partition of that interval from a to b, subintervals of width delta x of I. Then the length of that L, that length there, would be delta x of I squared. Let's go back to our picture here. This length here would be this squared, the square root of this squared plus that squared, right? That would be Pythagorean angle, that would be your hypotenuse there. Okay? Now, let's think. The delta x is just that delta x there. Delta y here is the R1 squared minus R2 squared. I mean, R1 minus R2. That's your delta y. Because it's just that difference in those radii. Okay? So that's a okay. Whatever it is, it's just the delta y sub I squared. Now look at this again. That looks awfully familiar. That's basically coming up on your arc length, right? This is exactly how we did the arc length, okay? So this part was just like we did before, the square root of 1 plus dy dx squared, okay? That is the arc length thing. Only now we're talking about the lateral area of a frustum of a cone. It's the arc length. That's all it is, okay? Now, your R sub I here, going back to this thing, was that on the last slide? I think it was. No, it wasn't. Was it on the there it is. S equal 2 pi RL. That's the surface area of that. Where R is the average of those two. Okay? Now we go back here, and it's 2 pi times that average R, the average length in the middle of R, times your delta L. Okay? Now it's just a little segment of that. The delta L is exactly what we were getting for. It's your arc length, the delta arc length. Now this R is your alpha of D. Now, from the R be the average radius of the frustum, R sub I, frustum, by the intermediate value theorem, a point DI exists on the ith subinterval such that R of I is equal to F of D of I. Okay? Okay. The lateral surface area would then be that F of D. So it's 2 pi R of I, which would be alpha of some value in that interval, alpha of D of I. Times your, basically, your arc length. Yeah. Okay. That's what you got. And it makes, so the mean value theorem, now they introduce a C, okay? A number C of I exists between x of I minus 1 such that F prime of C of I is exactly equal to that. Goodness, they get it so complicated here. When you finally get down to it, it's 2 pi times the radius. This is representing the radius times your arc. If you just remember that, all these intermediate steps take you through so much mess, but if you just think about it's 2 pi, the 2 pi R, where R is the distance. Now this is if it's above the x-axis. If this isn't above the x-axis, it's a different R. But if it's the distance above the x-axis, that's your f of x, that's the y value. Okay? So that's your radius that you're going around the x-axis here. Of this part of that arc length, okay, this is exactly the expression for the arc length. So you take that arc length, whatever that arc is, it can be curved or whatever. It doesn't need to be a frustum of a cone. That arc length revolved around there. 2 pi R is your radius, but R is the function value if it's around the y-axis. I mean, revolving around the x-axis. That would be exactly what your radius would be, the average radius there. And so it's just this. In a similar manner, the graph of the F revolved around the y-axis. Then if you have y as x as a function of y, then yeah, 2 pi x now, that's how far out you go there. And why is that exactly the same? Because that arc length is the same whether you measure it this way or that way. I mean, it's the same thing. So this is the same arc length. So instead of alpha of x here, you put x here if you're revolving around the y-axis. So it's 2 pi x times that arc length. You can keep the dx's, you don't need to go to dy's. That's sort of surprising, but you don't. You really don't. Okay? So, in these two formulas for S, you can regard the products, 2 pi alpha of x and 2 pi x, as circumferences of the circles traced by a point xy, that's what I was trying to say, on a graph of alpha as it's revolved around the x and the y-axis. Okay? In one case, the radius is alpha of x, the other case is r is equal to x. This is the one revolving around here. Your radius is f of x. When you're revolving around here, the radius is just x. Now, if you're revolving around something else, x equals -3 here, it would be the radius. the 2 pi, why did I even introduce this? Let's wait till they bring it up. What I meant to do is put the line down here, y is equal to here. Then your radius would be f of x minus c. If c was here, if c was up here, it would be f of x minus c. So it would just be f of x minus c if it was a point c around the line y is equal to c. It's just that c couldn't intersect that. Anything here below or up here, it would be alpha of x minus c. It would be c minus alpha of x. And that would be your radius. So you just have to adjust if it's somewhere else. Same thing here. If this axis were over here or over here or in here, then you just do x minus whatever that would be, d or f or whatever. But they haven't gotten there yet, so let's not worry about it. Sorry. So here's the definition of the area of a surface of revolution. If y is equal to f of x has a continuous derivative on the interval a to b. What does that tell you? Smooth, continuous function. If it has a continuous derivative, the function must be smooth and continuous. The curve has to be smooth and continuous. So if that's the case, then the area of the surface of revolution for revolving around the horizontal or vertical axis is S is equal to 2 pi integral from a to b, that's where you're doing, r of x, that's your radius of x, times the arc. Okay? So the 2 pi of the radius, okay. Now if that's going around the x-axis, the radius, this is your f of x. If it's going down around anything else parallel to the x-axis, it's f of x minus something, f of x plus something. You know, you just have to adjust that for the radius. Okay? R of y would usually be x plus or minus something. So this would be f of x plus or minus something. This would be x plus or minus something. Whatever your radius happens to be. But the rest of it is exactly the same. Now, why? Oh my word. Okay. Why did they change? See, here they said if it's around the y-axis, keep this the same and just do x rather than f of x. Okay? That kind of makes sense because that arc length is the same length whether you're revolving it around this way or around this way. The arc length is the same. Okay? But then when they got to over here, they changed it to the radius is a function of y, and this x is a function of y. And why would they have done that? Just let that be x, you know, plus or minus wherever you're revolving from. This also works, but okay, I guess if originally your function was given that way, not given this way, and you're revolving, then this would be how you have to do it. So I guess that's why we did it. It was so much simpler keeping just x there. All right, let's see what example 6 does for us. Find the area of revolution. Let's see, is this the actual next slide here? Okay. Did you finish? Okay, thank you. Okay. example 6 is the next one. There was one thing they did at the bottom of the previous page. Ah, good deal. Here's Vince. What's that?
My power was out this morning.
Oh. We're in Chapter 7, of course, Application of Integration, still in 7.4, and just about to wrap it up if we don't get wrapped up first. We got time, though. Yeah, we got plenty of time. Okay. But what I was going to say, let's go back to this. I thought they were going to have this on the slide, but they don't. Like I said, this part here was exactly what your integral was for your arc length, right? And because of that, and this is the incremental arc length, right? Because you've got the d's in there, that's incremental, that sometimes they refer to this as ds in either case here. And they give that at the bottom of page 479, 2 pi integral from a to b of r of x ds, where ds is the shorthand for all of that. Or the other one was 2 pi from integral from c to d of r of y ds. Where ds is these two things, either one of them, whichever you were given to begin with. You may see that coming up later. That's why I wanted to point it out now. I haven't taught this part of the book before, so I don't know if they're going to come up with it. Other books, texts would have. Let's see if they do. Okay. Fine. So here's example 6. Find the area of the surface formed by revolving the graph f of x equal x cubed on the interval from 0 to 1. And that's sure enough the cubic function. You remember what the cubic function looks like. It comes up from here, curves in here, it goes up here. This is going from 0 to 1. It's not a parabola, it's that part of the cubic function, but that's fine. On the interval 0 to 1 and x, okay? About the x-axis, so we're doing exactly what we did before, as shown here. Okay, so if it's about the x-axis, what is our integral? Doing dx's, the x's are going from 0 to 1. So I filled in that part for you. Knew that would be hard, so I did that part. Now what's the rest of it? This is surface or revolution. Oops. 2 pi, I didn't leave enough room for that. You got the 2 pi out front, because it's 2 pi times the radius. And what's your radius in this case? We're doing it about the x-axis. So the radius here is simply your f of x. There's your f of x. X cubed. 2 pi r, that's that part. Times the square root of 1 plus, what goes in there? F prime of x is equal to what? 3x. One little other part. 3x squared. Okay. And then what do we have to do with that?
And let's square that.
Square that. And that would be?
9x
to the fourth. Perfect. And then what do we do with that?
We put that under.
Now add 1. Don't forget to add 1.
Okay, I thought we already added 1 there.
Okay, add 1. And then we put that under a radical. Oh, a big boo hiss here. Okay. That's going to be under the radical. Oh, okay. You saw we already had the 1 plus. Okay. 9x to the fourth. Okay. Oh, not too bad, is it? Why not?
We have calculators.
No, we don't need a calculator yet. We might later, but not now. I'm guessing we may not even need one. 2 pi. How would you do that integral? Oh my goodness gracious. See, these tend not to be as hard as the surface area, as the arc length. What can you do? This is back on what? Was this test 1 or test 2? We did tons of these.
Trying to get rid of
This is trying to integrate them.
Substitution?
Substitution! All right. What do you want to substitute?
Let u equal
1 plus 9 x to the 4th. The innermost part, the most difficult part of the integral, right? Okay, then du is equal to what?
X to the 4th. 9x to the 4th? Is that 9x?
Guess it. 36x to the 3rd. Okay. Whoa. Every time I do this, it messes that up somehow. I don't know. Okay, there we go.
Can you walk me through the 36x to the 3rd?
Say again?
Can you walk me through the 36x to the 3rd, please?
Okay. Yeah, I want to get rid of the 36, so we'll divide both sides by 36. Is that what you're saying?
No, I was asking you, how did you get 36?
Oh, how did I get 36? U is 1 plus 9 x to the 4th, the innermost part, right? Got that?
Yeah.
Now what's du? Derivative of 1 is 0. Derivative of 9x to the 4th would be the exponent times the coefficient times the thing, power rule, exponent times 1. Right? That'd be 9 times 4 is 36, x to the 3rd. Good? Okay. Now, then I divide by 36 so I can get my x dx. Right? Oh, we did leave off that, didn't we? Dx. Yeah, that's okay. Dx. 36x cubed dx. Divide by that, and that gives you x cubed dx. And now we have a 2 over 36 is on the outside, which is a 1 over 18, right? Pi. And now it's going to be the integral from, and this is the du part with the 1 over 36 out front, and that would be u to the, I don't like to write the square root sign, so what do I write that?
U to the 1/2.
Well, u to the 1/2 du. Whoa, we don't have any unit limits, though, do we? Don't we need some? Because these are limits for x, we need limits for u. So when x equals 0, what is the lower limit for u? No. Just plug in. U is equal to 1 plus 9x fourth, right? Plug in a 0 for x. What? So the lower limit's going to be 1, and the upper limit's going to be? Say again?
10.
10. Perfect. All right, there we got our limits for u now. So let's go to town with this. This will be pi 18ths antiderivative of u to the 1/2.
One half u. I'm confusing myself here. The u to the 3 halves over 3.
Over 3 halves, which is same as times 2/3. Remember?
Right.
Okay. Over 3 halves, which is same as times the reciprocal of that is 2/3. And we're going to evaluate that from 1 to 10. Okay? So that's going to be pi 18ths. That's out front. Now let's plug in a 10. And what do you have? Woo! Woo! Oh, man. Let's pull out the 2/3. Can we just do that? Because that's going to be everywhere. So that's it. 2 will go into 18 9 times. 9 times 3 is pi 27ths. Got that? So that's going to be pi. Oh, my eraser didn't work. That was a sleight of hand there. Did you see what I did? Let's pull that 2/3 out and put it with the 18. Well, the 2 will go into 18, 9 times 3 times 9 is 27. So that's pi 27. That way I don't have to worry about all those fractions. Oh, they're the same everywhere, so get them out on the outside. Okay. Now let's do the square root of 10 cubed, which basically is the square root of 1,000. Okay? Minus 1. And that does look bizarre, doesn't it? Let's see if we can simplify it a little bit. Pi 27ths times 10 root 10 minus 1. I think that's the answer. They left it as 10 to the 2/3 minus 1. I'm pretty sure that's what that gives you. So if someone will do 10 times root 10. Anyone got a calculator to do that? Let's start with here. 10 times root 10, and then subtract 1 from whatever that is. It's going to be 30 something.
30.6227766.
Okay. Multiply that by pi and divide it by 27.
3.563.
Hey, got the same thing they did in the book. Way to go. Okay. To me, that's easier than 10 to the 2/3 power, 3/2 power. Maybe you could do that easily on your calculator, but I could do 10 root 10, just not in my head, but yeah, without too much struggling with the calculator. Okay. It gives the same answer. Okay. That was example 6. Let's see how they do example 6. Okay? Let me erase what I've got, though I don't think they're going to continue on this slide. Anyone need it up there a little longer? Is it making sense, or is it all magic? Let's see if they can make it make a little more sense. Okay? The distance between the x-axis and the graph of y is your function. X-axis and that's f of x. Okay? So your radius of x then would be f of x, which is what your I think we did all that. The radius of f of x, f prime was 3x squared. We did that. So the surface area would be 2 pi times that radius, which is your f of x. Integral from a to b, which I take from 0 to 1. The f of x is x cubed. Square root of 1 plus 9x to the 4th. That's f prime squared. Okay. So that gives you 2 pi integral from 0 to 1 x cubed. That's your radius. Okay. Square root of 1 minus 1 plus that. which is just what we said. Now they rewrote. Okay, they're doing several things here. That this way. They threw in this, knowing what the next step is going to be, but without telling you what the next step is yet. So this to me is magic. But they knew what was coming, so they did this. They rewrote this as the square root of 1 plus 9x to the fourth, wrote that as 1 plus 9x to the fourth to the 1/2 power. Now, looking ahead, they're going to do a substitution just like we did of let u be this, and then du would be 36x cubed. Way before we got there, they knew it was going to be that. So I think that they're showing magic here. Well, to get this to be 36x cubed, they divided by 36 also, to keep that the same value. Okay. To me, this is a magical way of doing it, because you have to anticipate your next step before you take it. Okay. But we did that too. I mean, we got to the same result. That's pi over 18. And then that would be that to the 3/2 power. They didn't actually do a substitution, but they sort of did a substitution. So they left it in x's. I think it's far easier to see to do a substitution. That's me, okay? I would have written that as 2/3 of that. And then magically they say, but this is, if you had written this as 2/3, then you can see where they get pi 27. Doing it this way, you have to really have some faith in them to get that. But that does come out being pi 27 times this. So that is indeed your answer, okay? Same thing we got, only they went about it. If you thought mine was magical, theirs even more magic, I think. Though I know what they're doing every step, but you have to know that for it to make sense to you. Okay? And that answer is about 3.563. Oh, wow. I don't believe this is the clearest way of doing it. It certainly is correct, but I don't think that's the clearest, because you have to backtrack and say, well, why did you do that? Where did that come from? Well, you knew you were going to need it, Well, no, that's not very fair. Okay. All right, and that was the last. Oh, no, there isn't. There's example 7. So let's go back, and we're going to do example 7. Is that okay? Do we have time? Yes. Don't we? All right, let's do example 7. To find the area of a surface formed by revolving the graph of f of x equal x squared, okay, on the interval 0 to root 2, about the y-axis, okay, as shown in the figure. Okay, so what they're doing here, I'm going to try to draw a little simple figure. Here is the parabola, y is equal to x squared, right? And I had to look to make sure the x value is what's going 0 to pi half. I mean, 0 to the square root of 2. Okay? And then the square root of 2 squared would be 2, right? So this is, and on the y-axis you're going from 0 to 1, on the x-axis you're going 0 to root 2. Okay. This is the x-axis, okay? X values. All right, and you're revolving that around the y-axis. Now, the one way they said to do this would be the integral from 0 to pi half of root 2. I'm sorry, why am I saying pi half? 0 to root 2 of x times your arc length. Okay? Let's see if that would work. Because that would certainly be easier, I think, than the other way. So let's try that first. Your surface area will be 2 pi times the integral from 0 to root 2 of x times the square root of 1 plus f prime squared dx. Okay? At least on the surface, that seems like that would be easier. All right. So, first thing we got to do is, okay, f prime of x is equal to 2x. Okay? And then that thing squared is 4x squared. Okay? So our surface area now would be 2 pi times the integral from 0 to root 2 of x times, let's write it as a radical, as a exponential form rather than a radical form, be 1 plus, you just told me that was 4x squared to the 1/2 power. Didn't you say? Dx. Let's see if this will work.
Should that not be an x squared out front?
Why?
Because I thought that,
Okay, yeah, okay, I see now what you're saying. If it was revolved around the x-axis, that would be an x squared.
oh,
But, okay, if you go back, let's go back quickly here. Right here, this is the one I'm trying to use now. S is equal to 2 pi integral from 0 to root 2 of x, this. Because this is going around the y-axis, your radius now is just going to be the x, how far you are from the y-axis.
yes, sir.
And that's what's going around. So that's why it's an x. If it was that one up there, it would be an x squared. You're absolutely right. Okay. I'm not sure this is going to work. They said it would. That's why I want to check it and see. Okay? Yeah, here we are. So, I think we got it set up. What will you do to solve this? Substitution. Exactly. What would you substitute? Perfect. Then
du
8x dx. Okay. I don't want the 8 in there, so I'm going to divide it out. Okay. So when I change this from dx's to du's, that will be dividing that. So it's 2 pi divided by 8, which now becomes pi fourths, right? The integral. Now let's see what the root 2 becomes. Oh, well, when x is 0, u is, or u are, 1. And when x is root 2, x squared would be okay, 4 times, yeah, x squared would be 8, plus 1 is 9. Okay. Everybody see that? These are the limits for u now. Limits for x was this, but when u is 1 plus 4x squared. When x is 0, that would be 1 plus 0, so it would be 1. When x is root 2 squared is 2. 2 times 4 is 8, plus 1 is 9. So that's the limits for the u. Okay. All right. And your, did it come back? Okay. Your du is, dx is 1/8 of u. We already pulled the 1/8 out front. So this would just be u to the 1/2 du. Right? Agree or not? Okay. Now how would we integrate that? I'll do the 5/4. Help me, somebody.
So the 1/2 u to the 3/2.
Okay, I agree with the 3/2 part. U to the 3/2.
Oh yeah. I was sort of combining.
Yeah. I mean, take a little derivative, a little bit of integral. Why not? Antiderivative. Yeah, just throw them all together, however you want to.
It just winds up at 0.
Yeah, right.
And, so it'd be u to the 3/2 over 3/2.
Which is the same as
2/3
times 2/3. Okay, and again, I'm going to take that fraction out and make that 2. So this will become a pi/6 now. You see what I did? Okay, so this is going to be, yuck. Okay. Let's evaluate this from 1 to 9. Okay. Well, this one's a lot easier, believe it or not. That's pi/6, that's out front. Okay. Now, so I took the 3 out of there too, so it's not in there anymore. So if u is equal to 9, first take the square root of 9, 3, and then cube it, 27, minus 1. So this will be pi/6 times 26, which would be 13 pi/2. No, I did that really badly. What in the world am I doing here? Yeah, 13, I got that part, that's pi/3. 13 pi/3. Whew. 2 will go in the 6, 3 times. So we get 13 pi/3, that's what they got. And if you got a calculator, punch that in. It's a little over 13, between 13 and 14. Oh, I knew that 2 will go into 26, 13 times 2 will go into 6, 3 times 5, 13 pi/3. That would be your surface of revolution. That's not the volume, that's the surface. Because pi is 3.14, so pi over 3 is just a little over 1. Something a little over 1 times 13 is something a little over 13.
It's 13.61.
That's exactly what they did. And they did it the same way we did. So, no, they kind of did. They just love skipping a bunch of steps at the weirdest places, too. All right. What do we? Oh, we've already passed overtime. Sorry about that. Homework exercises. Do number 5. Okay, then do any of the odd. Do either 7 or 9. They're both 5's a calc chat. 7 or 9 are both a calc chat. 7's a calc view. Then do any of the odds 11 through 19. They're all at calc chat. Any of the odds 21 to 29. They're all at calc chat. Do 31 is a calc chat. Do 33 is a calc chat. Do either 35 or 37, they're both at calc chat. Do any of the odds 39 to 43, they're all at Calc Chat. 39's at Calc View. Do 45 or 47, they're both at Calc Chat. 45's at Calc View. Do 49, it's at Calc Chat. And then explore whether you want to do 51 or 53 or not. They should both be at Calc Chat. You could think about doing 55 if you'd like. It should be at Calc Chat. And then any of the odds, 57 through 61, it looks like, they should all be at Calc Chat. Well, actually, no, continue that through 63. They should all be at Calc Chat. Then do either 65 or 67. They should be at Calc Chat. And then try 69 and or 71. They should both be at Calc Chat. And we'll start next time with, finally, work. Okay? But y'all can do that between now and then, too. Okay. So that will be 7-5. Boy, this was one long section, wasn't it?